Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
Building traditional software is like tuning an engine, but generative AI is like a fluid dynamic simulation. It is inherently chaotic. In traditional machine learning, we relied on deterministic metrics. We measured accuracy, precision, and recall, clear, static numbers. Large language models break that framework entirely. They operate on probability, generating text one token at a time. This non-deterministic behavior means the exact same input can yield wildly different outputs. This image captures the core reality of engineering with LLMs. Evaluation is a decision-making process under uncertainty, not a benchmark exercise. We are managing ongoing operational risk. This uncertainty creates a unique engineering threat. An LLM can confidently produce an answer that is grammatically perfect, stylistically authoritative, and contains deep factual errors. We call these silent failures, the primary adversary in LLM development. This slide illustrates the transition to LLM evaluation. The red box highlights the threat. Unlike traditional software that crashes, LLMs produce syntactically valid outputs containing severe factual errors. Because the code executes successfully and no error logs are generated, these hallucinations bypass standard software monitoring entirely. To your server, everything looks perfectly fine. Moving to generative AI requires abandoning the pursuit of high benchmark scores. The goal is now architecting systems designed to hunt down and contain these invisible failures. To catch these errors before they reach users, engineering teams must adopt strict operational rules. This grid shows the core principles of LLM engineering. The top right quadrant is the most critical. Evaluate the system. Stop evaluating the base model in isolation. A foundation model is just a component. You must test the entire application infrastructure around it. This diagram shows how evaluation scales outward through 3 abstraction levels. Level 1 measures isolated model capabilities. Level 2 measures the complete architecture, including retrieval systems and parsers. Finally, Level 3 measures business impact, operational return on investment, and real-world safety. A base model can achieve perfect scores in an isolated Level 1 test, yet fail completely in a Level 2 production environment due to poor data retrieval or a brittle orchestration layer. Let's examine Level 1 directly to understand why base model testing is insufficient on its own. This graphic maps standard benchmarks into 4 core areas. However, the red column exposes severe vulnerabilities. The highest risks are data contamination, where test answers leak into training data, and models simply overfitting to leaderboard metrics without gaining actual capability. Relying on compromised Level 1 scores creates a direct legal liability as governments begin to codify AI accountability. This chart details foundation model compliance against the draft EU AI Act. Even the most heavily funded models score poorly. Notice the concentration of failing grades in data governance and risk mitigation. The law is forcing a shift toward radical transparency. High benchmark scores offer an illusion of competence. To build applications that are legally and operationally ready, engineers have to migrate out of Level 1 testing and into the surrounding system architecture. That brings us to Level 2, evaluating the system. Before writing a single line of orchestration code, you need a robust evaluation plan. This diagram outlines 4 pillars for evaluation: inventory capabilities, map costly failures, set acceptance thresholds, and define escalation policies. The red risk model pillar maps the specific financial and reputational cost of silent failures, like hallucinated legal advice or privacy leakage. With a plan established, we can evaluate the architecture itself. The most common Level 2 design is the Retrieval Augmented Generation, or RAG pipeline. This row tracks a RAG system's data flow. The LLM is entirely dependent on retrieved context quality, measured by context precision and recall. We also use MRR and MAP to evaluate the speed and consistency of the search process. If your system has poor precision and recall, the underlying intelligence of the base foundation LLM is completely irrelevant. It is being fed garbage data, and it will simply hallucinate at scale. Evaluation becomes even more complex when we move from simple RAG pipelines to autonomous agentic systems, where the LLM actively orchestrates external tools and updates its own memory store. This schematic shows the 3 lenses required to evaluate an agent. You have to audit its internal emergent behaviors, measure the computational efficiency of its engineering, and assess the subjective quality of its interaction with human users. But how do we actually measure these subjective multi-step interactions reliably? We have to deploy a specific spectrum of measurement tools. This maps the measurement arsenal, from slow, accurate human-in-the-loop scoring to fully automated metrics using LLMs as judges. LLM judges suffer from verbosity bias and favor their own model family. They require continuous calibration against human baselines. Adversarial testing balances a system's attack success rate against its false refusal rate. The red box identifies the over-refusal trap. With excessive guardrails, the model triggers safe abstentions for completely benign user queries. A system locked down by hypersensitive guardrails will not generate offensive content, but it will also refuse to do any actual work. Evaluation is an engineering compromise between safety and utility. We finally arrive at the Level 3 abstraction, business-level production reality. Deploying an LLM system into the real world guarantees it will encounter new, unanticipated failure modes. This table maps the most dangerous production failures. You have to monitor for prompt regressions caused by subtle template tweaks, latency spikes that break downstream dependencies, and data drift, where user input shifts away from your training distribution over time. Catching these failures as they happen requires instrumenting a comprehensive observability pipeline across your entire architecture. This diagram shows the interlocking chain of end-to-end observability. You must monitor formatting at the user input layer, relevance at the retrieval stage, performance during LLM inference, schema conformance during output parsing, and finally, direct user satisfaction. Implementing this level of monitoring happens in 4 escalating stages of sophistication. This chart breaks down the progression. You start with Stage 1 threshold alerts for response times, then build Stage 2 statistical anomaly detection. Next is Stage 3, drift detection via vector similarity shifts, and finally Stage 4, tracking user feedback to measure real-world degradation. This progression demonstrates that evaluation isn't a gate you pass through before launch, it's a permanent operational cycle. This diagram maps the continuous loop. A system moves from offline evaluations against risk models through strict release gates into online A/B testing. It's then monitored for drift, generating new incident logs that feed directly back into updating your initial risk requirements. Embracing this continuous loop is the only way to tame the non-deterministic nature of AI. It is how you transform unpredictable probabilistic models into reliable, production-grade engineering systems.